Consider I am giving you two apple slices, one fresh and another dried, and I ask you to determine the glass transition and freezing point. As I mentioned in my earlier video, we need to know first whether the sample contains freezable water or unfreezable water. How to find this? Take samples from both slices as shown for DSC analysis. Please watch this video until the end and subscribe to our channel if you like this video. We could just run a DSC scan from room temperature to -90°C and then heating from -90°C to 300°C at a heating rate of 10°C per minute. This can give us an initial idea of the sample. First, we could run the dried slice. Any shift in the heat flow curve indicates glass transition. Any endothermic peak below 0°C indicates ice melting, that is reversible process as freezing, and an endothermic peak at higher temperature indicates solids melting. DSC heat flow for a dried apple slice shows as displayed in this diagram. We could observe a shift indicating glass transition and then an endothermic peak as solids melting and then a change in slope indicating degradation or compositions. We could observe the shift with two baselines as shown. DSC heat flow curve for a fresh apple slice shows a shift at low temperature indicating glass transition, then an endothermic peak below 0°C indicating ice melting, then endothermic peak as solids melting, and then a change in slope indicating degradation or structure building. Analyzing glass transitions is similar to samples containing unfreezable water. Please watch my another video as shown in the description box. Now we know the fresh apple slice contains freezable water since we observe ice melting endotherm, and we need to follow a specific procedure as I am going to discuss next. Most commonly, ice melting endotherm is considered a reversible process, thus melting is just opposite to the freezing, and then freezing characteristics could be determined from the ice melting endotherm. This is due to a lag period during cooling of the sample. First, look at the DSC endotherm as shown. If we draw a baseline toward the left by following the same slope, then it could intersect to the onset of the endothermic peak. This point is considered as an maximal freeze concentration melting temperature as Tm-A, and the onset shift of the baseline at the left is considered as apparent maximal freeze concentration glass transition temperature as Tg''A. This shift can be characterized by the specific heat change, that is del Cp. I am going to explain this later why I am defining it is an apparent. What is maximal freeze concentration condition? It is the conditions when all freezable water forms ice, and specific procedures of DSC need to be used to determine. The freezing point is considered as the point of maximum slope of the endothermic peak. This point is observed close to the freezing point as measured by a well-established cooling curve method. You may watch my earlier video on the cooling curve method. Links are given in the description box. The area of the peak indicates enthalpy, that is heat supplied to ice melting or heat needs to be removed due to freezing of water. The area indicates how much freezable water is in the sample, that is more enthalpy indicates more freezable water in the sample. In the case of a sharp peak, The peak temperature could also be considered as a freezing point. The area of the peak indicates how much freezable water is in the sample. If you dry the sample at different low moisture levels, then at some point it would be difficult to observe the ice melting endothermic peak. Since there will be no freezable water available in the sample, this indicates the end of freezable water in the sample. The freezing point decreases with the increase of solids content. If we plot the freezing point as a function of solids content, then freezing point would decrease with the increase of solids content. If we plot the ice melting enthalpy as a function of solids content, then we should have plot as shown. The amount of unfreezable water could be determined by extending the linear line to y-axis 0. X-axis shows at the solid content 0.86 gram per gram sample. That is, unfreezable water is 0.14 gram per gram sample. One point I would like to emphasize here, after solids content around 0.60 gram per gram sample, that is water content 0.40 gram per gram sample, it would be difficult to measure the melting or freezing process by DSC, since the process would be difficult to reach at high solid concentration. I am explaining this in the next slide. In order to grow ice crystals, water molecules need to overcome a few hurdles. These hurdles are diffusion of water molecules to the ice-water interface, energy potential required for the water molecules to cross barrier of the interface, release latent heat of fission and its transfer from the interface. Overcoming these hurdles depends on the concentration of the unfrozen matrix. That is, the process of equilibration will be very slow in the case of concentrated solution and will be difficult to achieve in the DSC. Therefore, at high solid concentration, the reliability of the freezing data would be limited, since freezing and melting is an equilibrium process and it will be difficult to achieve in the case of concentrated solution. If we measure the apparent maximal freeze concentration as a function of solute concentration, then it decreases with the increase of solids concentration and remains nearly constant around the solids content 0.4 gram per gram sample. Above 0.4 gram per gram sample, it remains nearly constant. Similar trend is also observed in the case of apparent maximal freeze concentration glass transition, that is Tg triple prime A. It remains nearly constant after solids content 0.5 gram per gram sample. In the case of dead syrup, unreliable DSC data observed after solids content 0.5 gram per gram sample. In an earlier example, we have observed apparent Tm' remain constant after solids content of 0.4 gram per gram sample. In this case, we could observe an even higher apparent Tm' after solids content 0.50 gram per gram sample. It is clear the equilibrium process could not be achieved. However, in most cases, solids content of 0.4 gram per gram sample would be the reasonably good option to be considered. It is not yet the ultimate maximal freeze concentration condition, since further time could be required to achieve equilibrium. If we measure the apparent maximal freeze concentration as a function of solute concentration, then it decreases with the increase of solids concentration and remains nearly constant around the solids content 0.4 gram per gram sample. Above 0.4 gram per gram sample, it remains nearly constant. In our earlier published papers, at solids content around 0.4 gram per gram sample, we used annealing Tm-1 for 30 minutes, and the annealed maximal freeze concentration is defined as the ultimate maximal freeze concentration condition, that is ultimate Tm- and ultimate Tg-. In order to determine ultimate maximal freeze concentration conditions, first we need to run an initial DSC to determine the apparent maximal freeze concentration conditions for solids content 0.4 or 0.5 gram per gram sample, that is apparent Tm- and apparent Tg-. Del Cp can also be determined to assess the relaxation and the fraction transforming from glass to rubbery, and enthalpy change during the melting process, that is del HF, and freezing point Tf. Second, perform the DSC run with annealing at apparent Tm-1 for 30 minutes and determine the annealed maximal freeze concentration condition, that is annealed Tm- and annealed Tg-. This annealing condition is considered as ultimate maximal freeze concentration condition since we use maximal possible solids content for DSC analysis, that is 0.4 gram per gram sample. These are marked as ultimate Tm- and ultimate Tg-. There is another advantage of the annealing condition. In some instances, an exothermic peak was observed due to relaxation of the sample before melting of ice. In this example of dead flesh, we could observe an exothermic peak just before melting of ice. In this case, it is very difficult to determine maximal freeze concentration condition, that is apparent Tm- and apparent Tg-. Annealing could solve this problem. I am showing them on the next slide. We could observe that the annealing condition could be removed the exothermic peak in the second cycle of heating. In summary, maximal freeze concentration is a condition when all freezable water transforms ice. First, we need to determine the apparent maximal freeze concentration condition. Second, annealed maximal freeze concentration conditions, and finally ultimate maximal freeze concentration condition. I would like to thank you for watching this video until the end. Please subscribe to our channel if you find this video interesting.